Welcome to month 3 of the BISTEC Hearts Academy engineer track. In month 1, you built your testing foundation, and in month 2, you built APIs. Today we're going deeper into the data layer that sits underneath everything you've built so far. Database design and optimization is one of those skills that separates engineers who build things that work from engineers who build things that scale. By the end of this session, you'll know how to design a schema that's clean and maintainable, write queries that are fast, and use real tools to diagnose and fix performance problems. Here's how today breaks down. Hour 1 is theory, schema design principles, and query optimization basics. This is the foundation you need before you start building. Hours 2 and 3 are the main event. A hands-on challenge where you design and build an e-commerce database from scratch. You'll create schemas, write migrations, build complex queries, and optimize them with real tools. Hour 4 is review and analysis, presenting your optimization results and examining different design approaches. Different people will make different decisions, and that's where the best learning happens. 5 concrete objectives for today. First, you'll learn to apply normal forms, 1NF through BCNF, to design clean, consistent schemas. This is the grammar of database design. Second, you learn when to use different index types. B-tree is the default, but there are times when hash, en, or keystone indexes are the right choice. Third, you'll learn to read explain and explain analyze output. This is the single most important debugging tool for database performance. If you can read a query plan, you can fix almost any slow query. Fourth, complex queries, joins, CTEs, and window functions. These are the tools you need for real reporting and analytics work. And fifth, you'll design and optimize an actual e-commerce database with proper migrations and seed data. Not a toy example, a real schema with real data. Normalization is the process of organizing your data to eliminate redundancy. The goal is simple. One fact in one place. If a customer's address changes, you update it in one row, not 50. First, normal form means every column holds a single value. No arrays, no comma-separated lists. If you have a tags column with electronics sale new, that violates 1NF. Each row should be unique. Second normal form says every non-key column must depend on the entire primary key. This mostly matters when you have composite keys. If you have a table with ordered and producted as a composite key, and product name only depends on producted, that's a 2NF violation. Move product name to the products table. Third normal form says non-key columns can't depend on other non-key columns. A classic example. If your orders table has zip code and city, the city depends on the zip code, not on the order. Remove city from orders and look it up from a zip codes table instead. BCNF is a stricter version of 3NF that handles edge cases with overlapping candidate keys. In practice, if you reached 3NF, you're in good shape for most applications. Think about this. Most production applications target 3NF, but normalization has a cost, more joins. Sometimes you denormalize on purpose for rate performance. That trade-off is one of the most important design decisions you make. Primary keys identify rows. Foreign keys enforce relationships. Together, they're what keeps your database consistent. Primary key rules. Unique, not null, and you should never change them. Use either serial for auto-incrementing integers or UID if you need globally unique IDs. UUDs are especially useful in distributed systems or when you're working with Azure SQL database and replication. One-to-one relationships are straightforward. A user has one profile. You put the foreign key on the child table, user profiles, with a unique constraint. This guarantees one profile per user. One-to-many is the most common relationship type. A user has many orders. The foreign key goes on the many side. Orders.userid references users.id. Many-to-many requires a junction table. Products belong to many categories, and categories contain many products. You can't model this with a single foreign key. The product categories table has 2 foreign keys, producted and categoryed, and their combination forms the primary key. Always define undelete behavior on your foreign keys. Cascade means deleting a user deletes their orders. Restrict means you can't delete a user who has orders. Set null means orders keep existing but lose their user reference. Think about what makes sense for your domain. There is no universal right answer. Indexes are how the database avoids reading every row. Without an index, a query on a million-row table reads all million rows. With the right index, it reads 10. B-tree is the default and handles most cases. It works for equality checks, range queries, sorting, and between. When you write tweak index without specifying a type, you get a B-tree. Use it for primary keys, foreign keys, and any column you search or sort by frequently. Hash indexes are the fastest for exact match lookups. Scenarios like find the session where token equals this value. But they can't do ranges or sorting. Use them for lookup tables or session tokens where you only ever do exact matches. Generalized inverted index is designed for composite values. If you have a JSON column, an array column, or you're doing full text search, GIN is what you want. It indexes every element inside the composite value separately. BISTEC, generalized search tree, handles spatial data and range types. If you're storing geographic coordinates and need nearest neighbor queries, or you're working with time ranges and need overlap detection, BISTEC is the answer. Think about this. Every index speeds up reads but slows down writes because the database has to update the index on every insert, update, and delete. Be strategic. Index the columns that appear in your where, join, and order by clauses, and nothing more. Explain is the most important performance tool in PostgreSQL. It shows you what the database planner intends to do with your query. Explain analysis goes further. It actually runs the query and shows you real-timing data. The most important thing to look for is whether you're getting a sec scan or an index scan. A sec scan reads every row in the table. It's fine for small tables, but if you see it on a table with a million rows, that's a problem. An index scan means the database used an index to jump directly to the matching rows. This is what you want for selective queries, queries that return a small fraction of the table. For joins, use a nested loop, hash join, or merge join. Nested loops are fast when the inner set is small. Hash joins build a hash table in memory, which is great for larger sets. Merge joins work on pre-sorted data. Cost estimates look like cost equals 0, 0 to 35, 50. The first number is startup cost, how long before the first row is returned. The second is total cost. Lower is better. The key is comparing costs before and after you add an index. Also compare actual rows to estimated rows. If the planner estimates 10 rows, it actually gets 100,000. The statistics are stale. Run analyze on the table to update them. Stale statistics are one of the most common causes of bad query plans. Let's talk about what to do and what to avoid when optimizing queries. Best practices first. Index the columns that appear in your where, join, and order by clauses. That's the single biggest win. Always use explain analysis before and after making changes. Measure, don't guess. Intuition about performance is frequently wrong. Select only the columns you need. Select star pulls every column, including large text fields and blobs you might not need. This wastes I/O and memory. Use limit and pagination for large result sets. Don't return 10,000 rows when the user sees 20. And batch your inserts and updates. One I insert with 100 rows is much faster than 100 separate I insert statements. Now the pitfalls. Don't index every column. Indexes slow down writes because the database updates them on every insert, update, and delete. Over-indexing is a real problem in production. Using functions in where clauses kills index usage. Null or email equals some value, you can't use a regular index on email. You need a functional index, or better yet, store emails in lowercase to begin with. The n+1 query pattern is one of the most common performance killers. It's when you query a list of items, then loop through and run a separate query for each one. One query for 100 users, then 100 queries for their orders. Use a J instead. One query, one round trip. Don't forget about VECU and table statistics. PostgreSQL Query Planner uses statistics about your data to choose the best plan. If those statistics are stale, the planner makes bad choices. Run analyze periodically, especially after bulk inserts, and always index your foreign key columns. Without them, cascading deletes are slow, joins are slow, and on delete cascade can lock your entire table. Joins, CTEs, and window functions are the three tools that take your SQL from basic to real analytical power. Joins combine rows from multiple tables. Inner join returns only rows that match on both sides. If a user has no orders, they won't pair. The left join keeps all rows from the left table and fills in nulls where there's no match, which is useful for finding users with zero orders. The example here joins orders and users on user id, filtering for orders over 100. In a real application, this is how you build almost every list view that shows data from multiple tables. PTEs, common table expressions, are named subqueries that you define with the with keyword. They make complex SQL readable by breaking it into logical steps. You can define a CTE called top buyers that aggregates total spend per user, then query that CTE like a regular table. You can define multiple CTEs and reference earlier ones from later ones. Window functions are the advanced tool. They let you calculate values across a set of rows without collapsing them into a single result. Round number gives each row a sequential number within a partition. Rank does the same but handles dice. Sum over gives you running totals. Think about this. The key difference from group by is that window functions keep all the individual rows. Right collapses them. If you want to see each order and its rank within the user's order history, you need a window function. Now for the main challenge. We're going to design and build a database for ShopStream, an e-commerce platform. The database needs to support users, products, categories, orders, order items, and reviews. That's at least 6 tables with a mix of one-to-many and many-to-many relationships. We'll be working with PostgreSQL. In production, this will be running on Azure Database for PostgreSQL or Azure SQL Database. For today, our local instance works fine. The challenge has 4 parts. Part 1 is schema design. Drawing an ERD, defining tables, and normalizing to 3 and F. Part 2 is migrations, version SQL files that create your schema and seed it with realistic test data. Part 3 is complex queries, revenue reports, product rankings, and user analytics using joins, CTEs, and window functions. Part 4 is optimization, running explain analyze, adding indexes, and documenting the improvement. You have about 2 hours for all 4 parts. That's tight, so manage your time carefully. Don't spend 90 minutes perfecting the schema and have 10 minutes left for everything else. Part 1 is schema design, and you have about 40 minutes. Start by drawing an ERD, an entity relationship diagram. Identify your entities, users, products, categories, orders, order, items, and reviews. Then draw the relationships between them. Users place orders. Orders contain order items. Order items reference products. Products belong to categories. This is many-to-many, so you need a junction table. Users write reviews on products. Define your columns with care. Think about data types, varchar for names, numeric with precision for prices, timestamp C for dates. Add not null where appropriate, and check constraints where they protect your data. Price must be greater than 0. Rating must be between 1 and 5. Normalize to 3 and F. No repeated groups. No partial dependencies on composite keys. No transitive dependencies between non-key columns. If you choose to denormalize anything, like storing a computed order total, justify it in your documentation. Part 2 is migrations, and you have about 30 minutes. Create version SQL files. 001 create users. SQL 02 create products. SQL, and so on. Each file should be runnable independently and idempotent where possible. After your schema is in place, seed it with realistic data. At least 50 users, 200 products across multiple categories, 500 orders, and plenty of order items and reviews. The more data you have, the more meaningful your optimization work in part 4 will be. Don't forget indexes on foreign key columns. Every foreign key should have a corresponding index. Also index frequently searched columns like email and product name. Part 3 is complex queries, and you have about 30 minutes. Now that you have data in your tables, write queries that extract real insights. Start with a revenue report. Calculate monthly revenue using date trunk to group by month, joining orders and order items to get line item totals. Next, top products. Use a CTE to aggregate sales per product, then rank them using the rank window function. Show the top 10 products by revenue. User analytics is where it gets interesting. For each user, calculate their average order value, their total lifetime spend as a running total, and the date of their last order. This combines regular aggregation with window functions. Finally, an inventory report shows a left join between products and order items to find products that have never been ordered. Collies handles the nulls, so products with 0 orders show 0 instead of null. Part 4 is optimization, and you have about 20 minutes. Take each query from part 3 and run explain analysis. Record the execution time and the plan type, sec scan, index scan, hash join, and so on. Now add strategic indexes. Focus on your slowest query first. If the revenue report is doing a sec scan on order items, add an index on the columns used in the layer and join clauses. Run explain, analyze again, and document the before and after. Your goal is at least a 5x improvement on your slowest query. Composite indexes. Indexes on multiple columns are your friend here. An index on user, read and created add together, can serve queries that filter by user and sort by date in a single index lookup. 5 deliverables all required. Submit them via your GitHub repository. First, your ERD diagram, a visual representation of your schema showing all tables and their relationships. You can use any tool you like, DB diagram, IO draw, IO usage chart, or even pen and paper photograph. Save it as doc.cert engine. Second, your migration files in the migrations directory. Version ordered SQL files that create your entire schema from scratch. Someone should be able to run these in order and have a working database. Third, seed data in the seeds directory. Realistic tested data, at least 1,000 rows total across all tables. Good seed data makes testing and optimization much more meaningful. Fourth, your complex queries in the queries directory. The revenue report, top products, user analytics, and inventory report. Each query should be in its own SQL file with a comment at the top explaining what it does. And fifth, your optimization report in docs optimization, ED. For each query, show the explain analyze output before and after optimization, the indexes you added, and the performance improvement. This is the most important deliverable. It shows you can diagnose and fix real performance problems. Remember, quality over quantity. A well-designed 6-table schema with clear documentation beats a 12-table schema that's poorly normalized and undocumented. That wraps up month 3. You now have the skills to design schemas that are clean, write queries that are fast, and diagnose performance problems using real tools. Every application you'll ever work on has a data layer. Whether it's running on Azure Database for PostgreSQL, Azure SQL Database, or any other platform, the principles are the same. Normal forms keep your data consistent. Indexes keep your queries fast. Explain shows you what's actually happening under the hood. The resources on screen are excellent next steps. PostgreSQL's official documentation is one of the best in the industry. Use the index loop. Com is a fantastic deep dive into how indexes actually work. Teach exercises. Com gives you practice problems and explain. Deliverable. Com helps you visualize query plans. Keep building, keep measuring. And remember, the best database design is the one that solves the actual problem, not the most theoretically pure one. Pragmatism wins. See you at month 4.